Yeah.
The bathroom ran out of stock in 3 days.
Okay, I didn't go to the computer to do this. Do I really need to show it, or do y'all trust that these do not turn out to be the same things? You trust? Okay, I trust. Right, so they are not the same. They do not give you the same value over the two different curves, even though the two curves connect the same 2 points. So in general, we do not have this idea of path independence. It's not here, all right? Path independence would mean that you get the same answer regardless of the path, which will come up. It does happen sometimes. So the answer to this is the integral depends on the path, right? So now what we're going to do is we're going to just extend these ideas now into a function of 3 variables. So instead of having our curve C living on a flat sheet of paper, our curve C is going to live in 3-dimensional space. All right? So if we have a curve that's smooth, if you go back when we talked about curves, vector functions, curves, smooth meant that they couldn't have any cusps on them. But as long as we have a smooth curve, and we can define our curve with the parametric equations, so we have an equation for x, y, and z, or a vector function which draws the curve, then the line integral of f along c with respect to arc length again is going to look very similar, right? It's basically the same formula that we had before. F is going to be evaluated at the different parametric equations. Then we have the arc length, but now it's 3-dimensional, so we've picked up a new piece in our square root, and it's with respect to t, and of course our limits of integration are still a and b. So very similar to this, right? But because we're in 3-dimensional space, we have a slightly different way we can write things, all right? And that is using this new notation. So this is what is the traditional notation, but here is an alternative notation. So what we're doing is we're saying, instead of saying f evaluated at the parametric equations, we say f evaluated at the vector function. So r of t is just the three component functions, right? X, y, and z. So we're just evaluating f at a vector function. This is weird, okay? Because you're evaluating a scalar function at a vector function. And then this piece right here, if you take the derivative of your vector function and take the magnitude of it, that's this. Okay, so the derivative of a vector function is the derivative of each component, and then the magnitude is the square root of each of the components squared, added together, square root. So this is just an alternative notation for this, all right? But now we're going to pretty much switch gears and be using this notation from here on out, all right? All right, so let's talk about if we have the line integral along C with respect to arc length, but now we're in 3-dimensional space, we also have 3 new line integrals, one with respect to just x, just y, and now just z. So now again, we've picked up a third one, haven't we? And just like before, these three will often appear together. And so if we ever see all 3 of them together, this is the notation we'll use. So just one integral symbol, then all 3 within the integrand, even though we have with respect to x, y, and z separately. So here's an example. Find this line integral along C, where C consists of the line segments from 0, 0, 0 to 1, 2, negative 1, and then from 1, 2, negative 1 to 3, 2, 0. So we have 2 curves again, right? They're straight line segments, but there are 2 of them. Now these I'm not going to be able to draw as easily because they're 3-dimensional space, right? So why don't we break this up? We'll say that C is the union of C1 and C2. C1, let's let that be the one that's connecting 0, 0, 0 to 1 to negative 1. And so let's come up with the vector function for C1. Line segment, right? So I'll use this. Now it's three-dimensional, though. So we're starting at 0, 0, 0. We still have to do you guys, right? We haven't done. Okay, we'll get you in a minute. And then we're going from here to here, so the vector from here to here is just that as a vector. And so basically we have t, 2t, negative 1, right? So that's our C1. And then our C2 is going to go from 1 to negative 1.
Shouldn't it be negative t?
Probably, I don't know. Let me see. Shouldn't it be what? Negative t, yes. Not negative 1. Negative t. And then there, on that one, that's going to be a little bit more work because that's not 0, 0, 0. So R2 of t will go from 1. Oh, t goes from 0 to 1. 1 to negative 1 plus t. What's my direction vector for this one? 2, 0, 1. 2, 0, 1. Which is just, let's see, 1 plus 2t, 2, the constant 2, and then negative 1 plus t. T goes from 0 to 1 again. So any questions on those? Are we we good with the line segments now? 2 or 3-dimensional? Got them? Okay, so now let's try and write this integral down. And we'll move on. Brenda, I guess you're up. Kind of, right? I'm going to leave that up there. I guess I'll do it right here. All right, so where do you want me to begin? You want to start with C1?
Sure.
Okay, go ahead.
So integral
Uh-huh.
from 0 to 1.
Okay.
And then what's the equation? So t squared.
Okay, so you're taking this x, right?
Yeah.
That's your x, so you're going to square it.
Um,
And then times,
times. Is it the derivative?
yep, dx, which would be the derivative of this, which is the derivative of that one. So 1 dt. Okay, but I'm not going to put the dt yet. Okay, we're going to work through all these. Okay, so that's that. And then I'll put times 1. Okay, plus,
Plus 2t, the whole thing squared.
yep, so we're doing this piece right here, which is 2t. That's our y. And then we're squaring it. Times 2, which is derivative of y. Or derivative of the y component, which is derivative of 2t, which is 2. And then plus, okay, z squared, negative t, and then that squared, and then derivative of that, right? Negative 1. Then all that dt, right? Okay. But then we're going to add to this going along C2. So why don't we just add it now? We're just going to put it all together. At the very end, we'll do dt. So you want to keep going, or you want to pass the torch? Okay, finish it up. So now we're on C2. So everyone keep in mind these. You want to do it? I don't care. This was along C1. Now we're going to go along C2. Don't worry, we're going to go back around. Go ahead.
So is it 1 plus 2t squared?
1. Okay, so 1 is coming from, you're doing this right here, right? Along C2, so we're looking at, where is C2? Right here? Okay, so that's your x. So you said 1 plus 2t squared, right? So there's your x squared times the derivative of that, which is 2. Are y'all following this? Okay, plus, keep going.
2 squared.
2 squared, but then times what?
0.
0. So that's actually going to have no contribution to the integral. Because this y is a 0. I mean, sorry, the y is a constant. So when you do the dy part, that's going to be 0. Okay, plus, I think we're at the last one, right?
-1.
-1 plus t, that whole thing squared, times
Times 1.
1, which is derivative of this with respect to t. So times 1. And then all of that dt, right? The whole thing dt. The reason we could do that and get it all in one integral is because at the end of it all, it's all with respect to t. And, very important, our limits of integration were 0 to 1 on both. Had this one been like, 0 to pi, then you would have had to have split it into 2 integrals, all right? But the fact that they were both from 0 to 1, they're all with respect to t, just crank it all out in one. And now this is just a bunch of polynomial stuff, right? You can just expand it, multiply it all out, collect like terms, and just do integration. Okay, good. We'll leave that one like that. All right. Before I do this section, or we're still in the same section. Before we do this, because this is going to be a major switching of gears now, okay? But before we do that, I'd like for us to discuss something. Let's say that I have, in 2-dimensional space, I have some curve C. And let's say that at every point on this curve, I can tell you the density of that curve. So I give you a density function. Okay, so you give me the x and the y coordinates, and I will tell you the density of that wire, let's say, sitting on a flat sheet. Then what would this integral represent? The mass. That'd be the mass of the wire. Just like in the previous classes when we had a lamina, some 2-dimensional object, if we took the double integral over the domain of the density function, right, with respect to area, then that gave us the density, that gave us the mass of the lamina, right? And then from that we could find the center of mass. Now that we have this idea of a line integral, if you give me a curve, right, a wire or something like that, and if its density is non-uniform and you give me the density function, then this will represent the mass. And then there's probably a formula for center of mass, and it's in your book, okay? If you want to find the center of mass of a wire, you can do it. But you'll have to reference your book. I say this because I believe, if I'm not mistaken, one of the mini exams might include a problem about finding the mass of a wire. Okay? And that's all I'm going to say about it, really. Okay? Now, you can do the same thing in 3-dimensional space. If you have a wire in 3-dimensional space and you have its density function at every point, then if you do the line integral over C with respect to arc length, you're going to get the total mass of the wire. It's just now your wire's in 3-dimensional space instead of 2. All right? So just be aware of that. I'm wondering if you're visually seeing it. Because, I see it a certain way. I don't know if everyone else does. I just said that we had a wire, and I gave you its density function. I'm wondering if you see it like this. Do you see the wire on the ground? And do you see the density at every point being like a z value that gives you a height at each point? The density at each point? And then what you're doing is you're finding the total area of the curtain, and the area of the curtain would then represent the mass. That's what's happening here. This is our surface, this is our domain, and the heights are our masses added up. Yeah?
Yeah.
Okay. Can't do the same thing over there because I can't really visualize that 4th dimension, but it's the same idea. All right. Now, so far, what we've done is we've said, all right, if we've got a function, a scalar function, and we want to move along a curve, right? We can add up things, and we get this answer which represents different things, areas or possibly masses or something like that. Now we're going to be doing line integrals over vector fields. All right, so go back to 10.3, and in 10.3 we defined, or we reminded you of the definition of work. Work is a number, and you can calculate the work by taking the dot product of F and D, where F is the force vector and D is the displacement vector. So if you take the dot product of those two vectors, you get work. So for example, if your displacement vector is here and your force is here, then the work done would be the dot product of those two vectors, which in this case would be 2.35. Where are you? There you are. Right? If I make my force and my displacement go in the same direction, I still get positive work, right? What happens when my force goes in the opposite direction as of the displacement? We're going to get negative work, all right? Because dot product, if the angle between them is greater than 90, we have a negative number for dot product. And what if they're orthogonal? You get 0, right? Your work you should get no work, right? If your force is orthogonal to your displacement vector. All right. So here's geometrically what we're trying to do. Imagine a point moving along a curve within a vector field. So we started class today with vector fields, right? Now we've got this point moving along a curve, but it's going through a vector field. If F is a force field, for example, magnetic or gravitational field, then the total work done by the field is the sum of all the work done at each point. So I have a picture that will represent what's going on. So here's our curve now, right? We've got this blue curve C. We've got a point that is going to be moving along this curve, but it's moving through a vector field. Remember, a vector field is just a vector at every single point, right? So what we do is we say, as it moves, can we calculate the work at each point? And then add that all up and get the total work done moving through the path. So we look at this one point right there. We say, all right, at that point right there, we have a force vector. That force vector is from the field, and that's the red one, okay? Then we have the displacement vector, right? If we want to calculate work, we need displacement. So the displacement will be the tangential vector for the path. So we have this, it's green, this is capital T. That's our unit tangent vector. It gives us the direction that our point is moving. So it gives us the direction of the displacement, right? The question is, though, how much is the displacement? Right? How much displacement do I have? I know that's the direction, but how much do I have? Well, imagine doing just a little infinitesimal movement, just a little tiny motion. Then that little infinitesimal direction, displacement, will be ds. It'll be the little infinitesimal arc length. Does that make sense? Yeah. So we come up with a formula for the work at just one point. And it looks like this. We can see that the work at each point will be the force, right, which is your vector field vector, dotted with the tangential vector, which gives you the direction, and then you scale that tangential vector back by ds. Remember, ds is just, it's going to shrink that unit vector down, because ds is a number, that's a vector, so you're scaling the tangent vector back to give you that little infinitesimal change. Does that make sense? Yeah? Yes? Okay. So if this is the work done at a single point, then what we want to do is add them all up, right? And that's where we bring the integral in. So the total work done will be the integral, the line integral, along the path C of f dotted with the tangential vector ds. That's our formula to calculate the work. Yeah? All right, so that's kind of our master formula for calculating the work done by a vector field on a particle moving along a path through the vector field. Now, remember, we said that to draw our curve C, we're going to be using a vector function, r of t, right? And that t will be restricted between a and b. So that gives us our C, right? And also remember, capital T is the unit tangent vector. We learned about that way back in chapter 10, right? So r of t is the curve. The capital T is the unit tangent vector to that curve. So with that said, we're going to be able to rewrite the formula. So look at the way this formula is rewritten. Okay, going back to chapter 10, the calculation of capital T was the derivative of r of t divided by its own length. Does that look familiar? Okay, that's what capital T is. And ds, we just saw a second ago, ds was that square root of all that crap, right? Square root of all that derivatives squared and all that, yes? But we just called that, we said it was the same as the magnitude of the derivative, right? What's great about that is that when you plug this into the formula, look, f is f, right? But look at what these two do. This is this, right? And this is this. And do you see they cancel? You see these cancel? And because those cancel, you get a final formula right here, which is the one we're going to work with, which is very clean and easy to work with. We have the integral from a to b. We have the field, the vector field, evaluated along our curve, dotted with just the derivative, which comes from right here, of the derivative of our curve function, dt. So if you're one of those people who's just like, give me the damn formula, there it is, okay? That's it. All right, so little last note here that's important. What do we mean when we say evaluating the field along the curve? It means we take our field function and in it we plug in our parametric equations. All right, so that's what this notation means. So let's do an example, all right? That's just me again saying, there's the formula. Okay, so this was the original formula we started with, right? For work. And I said this, just plugging things in and canceling, becomes this, yes? Okay, this, we are going to use this notation to denote this. So anytime we're talking about work, this is our notation. Just like when I wrote ds, when I wrote that, I said, okay, this is the notation we will use to mean the line integral along C with respect to arc length, right? When we want to talk about the work integral, the integral that gives you work, then this is the notation. It's the line integral along C of the vector field f dot dr. Okay, so this piece right here is just notation for that right there. So we are just, instead of writing that, we're calling that dr vector, all right? This is the first integral ever that you should have ever seen in your life where this is a vector, right? I mean, you know, your cal 1, f of x dx, right? Double integrals in here, f of x y dA, triple integrals, f of x y z dv, right? X, a, v, right? S. Everything has been scalar. First time ever that your differential is vector valued. And that's why it's dr with the vector, right? And that's because that part is a vector, right? This is a vector. All right, now, also note that if you reverse the path, if you reverse your path when you're calculating work, if you reverse your path, then it changes signs. All right? I think an example is in order. Find the work done by the gradient vector field of f of x y equals x plus y quantity squared on a path traversing the top quarter of the unit circle in a counterclockwise direction. All right, so we want to know what the work is, right? We want to know what the work is. So the work is, that's what we want, right? We want to calculate this. So there's a couple of things we need to know. We need to know C. We need to know the path, but we need it written as a vector valued function, right? R of t. And we need to know what the vector field is, all right? So what is the path? Let's start with the path. And where were we? Were we starting over? We starting over? Yeah, we're starting over. Okay, so you want the path? R of t is cosine t, sine t. That'll draw me unit circle. We want the unit circle top quarter counterclockwise direction. 0 to pi halves. Everyone agree? That'll draw me that piece right there. Unit circle, basically the first quarter of it, top quarter. I didn't say which quadrant. I should have specified, but yeah, we'll go with this. Okay, everyone happy with R of t? All right. You want to keep going? You know what the field is. What is the field we're working with in this problem? So I was hoping you would say that, right? Because what you did was you took the scalar function f and you said that's our field. But let's read through this. Find the work done by the gradient vector field of this function. So what is the gradient vector field of a scalar function? That's where you come up with the partials, right? So we have to create the vector field from this scalar function. Yes? So this R field is going to be the partial of little f with respect to x, partial of f little f with respect to y. That's what we need, right? Because this by definition is the gradient of little f. So the partial of this with respect to x would be, you can just do a chain rule, right? Like 2 comes out, 2 times all that, times the derivative of what's in here with respect to x, which would just be 1, right? So that's that. And then what's the partial of f with respect to y? Same thing, right? 2 times x plus y. That's it. Questions? This problem, they did not just give you the vector field, did they? They didn't. They said, oh, wait, hold on. Find the work done by the gradient vector field of this scalar function. So we had to extract the vector field from the problem. All right. We're going to move on, but I'm going to write out the formula over here just so we can use it. This means the integral from a to b of f evaluated at our vector function dotted with the derivative of the vector function with respect to t. So that's what this is. This is our work integral. This is what it is after we did that tangent shit and it all canceled out, right? This was the big thing right here. So you want to pick up? Okay. So we're going to do the integral now, right? Okay. Unless you want to do derivatives first. Do you think you can handle it all at one time? You think so? Yeah? Okay. Everyone ready for this? Okay, here we go. I'm going to squeeze it in right here. All right, so the work done will be equal to
The integral from 0 to pi over 2.
0 to pi over 2.
And then that, which is 2 to it.
So as a vector though, right? This is a vector. It's the vector
2 times
2 times
plus y.
x plus y. However, we're evaluating the function on the actual curve. So we're not going to use x and we're not going to use y. We're going to use cosine t for x and sine t for y. So it's actually 2 cosine t plus sine t, right, comma. Now the next part, yep, same thing. I'm going to run out of room, I think. Okay, that vector's done. Dot. And now a new vector, right? And that new vector is the derivative of this guy. So I think I'll have to squeeze it in like this. So here it is. Go ahead. Negative sine t, comma cosine t, and then dt at the very end. Now dot, right? Now we dot. Let's dot this. Dot products are the easy ones, aren't they? Dot products are the easy. You want to pick it up? So if we're going to dot these two vectors, you just do first component times first component plus second times second, right?
Right.
Okay, so you got it. This one, right? Times that one. So what would that be? There's a bunch of different ways I can write it, right? So how do you want me to write it? Do you want me to take the negative sine t and actually like distribute it through with the 2? Yeah? Okay, so let's do that. It would be 2 times that, which would be negative 2 sine t cosine t. And then the next piece would be, we have to do it here too, right? So negative 2 sine squared t. Plus, because it's a dot product, right? Plus, and now we go this times this. 2 cosine squared t. All right. And finally,
Minus 2 cosine 2 sine 2.
we did, wait, hold on, I lost myself. It was this and this, and then, so plus 2, right? Plus 2 sine t cosine t. I think that's it, right? That's the whole dotted out. Distributed everything out. And this all this is with respect to t. And we get a little lucky here, right? We get a little lucky that those two cancel. Unfortunately, this is not a minus. Boy, wouldn't that be nice if that was a minus?
Yeah.
Then we'd factor negative 2 out, but, you know, not everything's going to always go your way. Equals. All right, I'm going to take this one the whole way because I actually want a numerical answer for this. So I'm going to pull out, I don't know, just a negative 2 out of the whole integral. Now, you know what? I kind of want to leave the 2's there. You know what? Let's leave the 2's there because I'm going to power reduce each of these. Right? So if I power reduce sine squared, it becomes 1/2. So this is negative 2 times 1/2, and then 1 minus cosine 2t. And then I have plus 2 times 1/2, and then 1 plus cosine 2t. And then dt. Y'all get what I'm doing there? Just power reducing sine squared and cosine squared?
Yeah.
And that's why I left the 2's, because I realized those are going to just go away. So equals, okay, I still have a negative here, so negative 1, plus cosine 2t. And then I have positive 1, that's nice, plus 1, and then what, cosine 2t? dt. Ones cancel. And then now I have two of these, right? So now this becomes, now I'll pull the 2 out. 2 of my cosine 2t dt's. And now I'm ready for integration. Antiderivative of that is 1/2 sine 2t. But that 1/2 and the 2 are going to cancel out. So we should just get sine 2t. And then evaluating 0 pi over 2. So what happens here, if we plug in pi over 2 here, 2 times pi over 2 is just pi, and sine of pi is 0. Minus, and then we plug in 0, we get all that for nothing. We did all that for nothing. So there's no work done. Total work done is 0. All right?
The only work done was on our part.
Yeah, the only work was us. So what happened there? I mean, what's going on there if we get a total work of 0? Here's the actual problem. I mean, here's a picture of it. Can I erase this? Okay, so what's happening here is I want you to pay attention to the angle between the force, right, the vector field, and our tangential vector. So right now, I hope it's clear to you that we should have positive work here, right? And then right in here, we're getting negative, right?
Yeah.
So here we have a work is probably about 0, somewhere around there. And then we have negative work. But it's not symmetric, look. Like it's happening, like here's where we're having a switch, somewhere around here. Like everything from here was positive work, right? And everything over here was negative work. So why is it 0? Because, I mean, you would think it would have to be like in the middle here, wouldn't you? Or no? Yeah, because the force, the field itself is not necessarily linear like that. It might be doing something more over here than it was here. So it's hard to tell. You have to trust the math, all right? Now, what would happen if we would have done this problem, but we only did it over the first eighth of this circle, like if we went from 0 to pi over 4? Then we should get an answer, right? A positive answer?
Yeah.
And you could see in the integral, if you go to the very end, sine of 2t, and you integrate from 0 to pi over 4 instead, you're going to get a nice positive answer there. All right. Let me look at it first. And let me see if I'm ready to cut you loose on this one on your own here. Well, your field is just given to you, isn't it? So the only kind of real issue here is coming up with our curve, C. So we'll work this one together. We move around. Volunteers off the next table.
Us?
Sure. We're trying to calculate, this is the work integral, right? So we're trying to do this. We need to go back and probably start here with C again, right? What is our parametric or vector function representation of that?
So what you need to do, I'm trying to think, because in this case you would replace if you were just leave it as is, you would replace y as t, and then have the other t and the y end up equaling to 1 plus t squared.
So which is which?
So y is equal to t.
Other way. If it's solved for x, then y is t. If it's solved for y, the other way. Okay?
Yes, my bad.
So t here, and then 1 plus t squared there.
Yes.
All right?
That's your RT for the
Now, you have to give me a restriction on t, though.
Yes,
And t is the x, right?
correct.
So can you tell from the points I gave you?
Yes, it's going to be from negative 1 to 1.
Negative 1, 2, to 1, 2. Hold on. And this is a parabola that opens up, right? So it actually goes like this, like that. And we're only talking about this piece right here. This is our C, right?
Correct.
You with me? Yes?
I'm with you. I'm just writing this down.
Okay.
Because
So what's our restriction on t then?
it's going to be from negative 1 to 1.
Negative 1 to 1, because that's our, t is our x, and x goes from negative 1 to 1. So negative 1 to 1. Everyone happy? All right. While we're here, I'm just going to crank this out. Well, I'm not going to crank it out. Someone on that table is going to crank it out. 1, 2t. And we need that, right? Because in this formula, it's our field evaluated on the curve, dotted with the derivative of the curve, right? So we need that in this formula. I think we're there. I think we're ready to go. You want to keep going then? Yeah, go ahead. You got it. I think I'm ready for this. I don't think there's anything we're missing. Okay, so here we go.
We'll go from negative 1 to 1.
Negative 1 to 1.
It's going to be the field, so it's going to be like.
It's that thing, right? Okay, so let's start cranking it out. It's this big old nasty thing dotted with something, but let's get this here. So first part is,
It's going to be t over.
so you're saying x is actually this, right? So t over the square root of t squared plus y squared, but that's y. So we have to square that. I'll just put it in 1 plus t squared squared. Yuck. Okay, keep going. Now y,
1 plus t squared.
1 plus t squared
The same thing you got.
over the same thing over here. T squared plus 1 plus t squared squared. That's fun to say. The square root of t squared plus 1 plus t squared squared.
And then we check the vector 1.
Yeah, now dot that with the one that you said, 1, 2, t, right? dt.
So just be.
You want to keep going? All right, let's keep going. Ooh, my battery's about to die. My laptop. All right, so we've got integral, negative 1 to 1. No more vectors, right? We're about to dot, so everything should be scalar now. It'll be
That times 1, so
just this plus this times 2t, right? They have the same denominators, don't they? So I'm just going to put them together now, right? Because I'm adding them. So one denominator of square root of t squared plus 1 plus t squared squared. But on the top, I have t plus, I'm doing this times 2t, so 2t, and then plus this times 2t, which is 2t cubed. All that dt. Yeah? Give you a moment to look at that while I get my charger. That doesn't look like something you want to integrate, does it? At least not initially, right? Maybe it cleans up. I'm hopeful. Negative 1 to 1. 2t cubed plus 3t squared. You all right? That's the numerator? No, wait, what? 3t, not 3t squared. Yes, that's the numerator. And then our denominator. What is this thing? What is this thing squared? T to the fourth plus 2t squared plus 1, right? And if I put that together with this right here, I'm going to get t to the fourth plus 3t squared plus 1 dt. Does that help at all? Cancel where?
The part you just did before that.
Oh, like on each one? No. No, yes? I don't know, can you?
Because they use
Let me answer that question the way I used to answer that question for myself when I wasn't sure. What you're asking me is, can you do something like this? Is that what you're asking me? So, would that work? So this is 7, right? If you do it this way? Question mark. Is that true? Well, what is that? This is 9 plus 16. That's 25, isn't it? And that's 5. Obviously, these can't both be true. So, right? So we can't. Do you like that? Yeah. I used to do this all the time, okay, when I was a math student, because I wasn't sure at certain things. So I would just like, can I do that? And I try. And as long as I showed one thing where it didn't work, then I know I'm wrong, you know, right? Yeah, I'm done with that. All right. So while we've been talking about that over there, what's happening over here? Who's left here? Who's still standing? No one. Right? Everyone's sitting. Danny, are you up?
I mean, I try, like.
Oh, I'm just asking if you see anything there. I don't know. No? Anyone at this table see anything?
I think no, wait, no, that doesn't make sense. I thought I saw a way to separate them, but that wouldn't make sense if I did that. Because it would have to be 2t squared for that to work. You see
So now
you
here?
see what I was trying to do though, right?
I'm actually not sure.
I was originally thought, hey, separate them into but having like t squared plus 1, but however, it's not 3t squared instead of 2t squared, so.
T squared plus 1. What?
said, you mentioned a
Partial fractions?
Well,
Or, oh, yeah. This is just a U sub, everyone. This is all it is. It looks like it's not, but it is. The derivative of this, if we let U be what's under the radical, the derivative of this is 4t cubed plus 6t dt, right? And you almost have that here, right? You almost have 4t cubed plus 3t. It's off by a factor of 2. So if I divide both sides here by 2, I get 1/2 du equals 2t cubed plus 3t dt. So now, if I do this u sub, this new integral will become, well, what's this? What's that? That's half of du. So half of du. And then what's still there? On the bottom, we have square root of u, right? Which is really u to the negative 1/2. And then now you do your antiderivative, so you add 1. So when you add 1 and do all that stuff, you should get something like, I don't even know, u to the half. That's what you should get. That's the antiderivative. Plus a constant, but we're going to go to a definite integral anyway. So the antiderivative of this is, at the end of the day, square root of u, right? That's u to the 1/2. 3t squared plus 1, right? That's the antiderivative. And then we're evaluating that negative 1 to 1. And so when we plug in 1, so when we plug in 1, we get root 5. Minus, and then, is it root 5 again? Yeah. Oh no, we get 0 again? All that for nothing again? So every work integral you ever do is 0, right?
Exactly, perfect. That's right. Yes, that's correct.
It just happened to work out that way.
No, I feel like every single work equation has 0.
You can do that on the final. Just write a little note to me. All these integrals will be equal 0 because you said so.
Exactly.
And you'll be done.
I'll write that, and I'll get all my. I believe I'll get all my.
You get full credit.
Yeah, I'll get full credit.
All right, questions on the work integral?
That's true.
All right, so some slightly different notation. All right, some slightly different notation. Let's say that our force, our field, our vector field, instead of writing it, capital F like this, we write it in its 3 components, P, Q, and R, in its vector form, okay? Then let's look at what this becomes, all right? So this would be the line integral over C. Okay, what's F? F is P, right? Q, R. Yes?
Yeah.
And then dotted with what? That's your R prime of t, right?
Yeah.
So R prime of t, let's remember what this is. R prime of t is the derivative. Well, let me write down what R of t is some curve, right? I'll call it x of t, y of t, z of t, right? Then the derivative of this would be x prime t, y prime t, z prime t, right? Right, that's what this is. So that would be the next piece right here. So x prime t, y prime t, z prime t, dt. But now if I dot these, what do I get? Right? Those all added together. Multiply those and add them together, which is p dx, because when you have x prime t dt, that's dx. And when you have dy, dy is y prime t dt, and then dz is z prime t dt. So putting these together gives you this. And does that notation look familiar? That's basically your line integrals along C with respect to x, y, and z, respectively. So it's like you have a way of looking at this integral in terms of vectors, or you can look at it in terms of nothing but scalar functions. Because P is a scalar function, Q is a scalar function, R is a scalar function, dx, dy, dz are all scalars. So you wind up having like a vector form and a non-vector form. Does that kind of make sense? So we said earlier that this will appear later, right? Well, it's appearing. Here it is. Like this actually represents the work, okay? It's just another way of writing the work integral. Not sure if we'll do an example if it's, no, okay, so here we finally get one. Finally have a word problem to do. I'm letting you read that. A 180-pound man carrying a 20-pound tool bag walks up a helical staircase wrapped around a 20-foot radius cylindrical silo. If it takes 3 complete revolutions to reach the top of this 90-foot silo, then how much work is done against gravity? Yeah, so what is a helical stair? I mean, we have to understand some things in this wording, right? So we have this 20-foot radius cylindrical silo. So we have a silo that's 20-foot radius cylinder. Okay, so 20 feet from here to here. This silo is 90 feet tall. Right? and his ladder is wrapped around that, and it's helical, right? A helical staircase. So helical means it's going to start here, it's going to go around the backside, come back around, go around the backside, go back around like that, right? Helical staircase around this thing. It takes 3 complete revolutions to reach the top of this. Did I do that right then? He went around. There's 1 revolution right there. 2, not quite. Sorry, I didn't draw this properly. He's going to come around again. Raise this up. And come around again. Right there. That's going to be the top. See that? Okay. All right. Calculate the work. So if this were a physics class, you could do this very easily. This is a very easy problem in a physics class, because all you have to do is figure out the distance he went up, really. However, let's look at it from the perspective of Cal 3, all right? Which is, if we're going to calculate work, we need a field, okay? We need a vector field, and we need a path, all right? So, do we know the field? Do we know the field, and do we know the path? Those are the questions. So where are we at? Are you going to, yes?
So, like, you have to find RT, right?
Yeah, that would be our C.
So then would it be cosine?
Oh, you're going to go for it, okay? All right. R of t. She's going for the path of our man up the silo. Here we go.
Cosine t,
Cosine
sine t, and then t.
t, sine t, and then you said t? Maybe. I'll say maybe right now. Do you have any restrictions on t? You're on the right path. I mean, like you were almost there with this. Be careful though, because look at I think what you're doing is you're drawing circles like this, but you're trying to move up at the same time, which is this, right? Now, these circles have a radius of 1. That's not quite what you want, because this silo is 20 feet. So how can we adjust these? So I left a space here in front intentionally, because the number in front is always the radius of the circle. So if you do cosine t, sine t, the radius is 1. But if you do 20 cosine t and 20 sine t, now your radius is 20. So these two components by themselves are just going to draw me a circle of radius 20, right? Okay, now you need to move up, right? So you're using t.
So it'll be 90.
90t? What, maybe it'll help if we talk about what's the restriction on t. So you want to be able to draw this circle how many times? Because it tells you how many rotations it takes to get to the top. 0, not 3 pi. Each revolution is 2 pi, right? So 6 pi. Everyone okay with that? You're almost there. You're almost there. I think this is one of the hardest parts right here, because most people understand this is going to draw you circle radius 20. Most people understand that going from 0 to 6t means you're going to draw the circle 3 times. The part that people have trouble with is this, because you're supposed to wind up at the end of this time. You're supposed to wind up where? How high? 90. But right now, if t is 6 pi, you're going to wind up at 6 pi high. Right? And you don't want to be at 6 pi, you want to be at 90. So how can you start at 0 and end up at 90 by plugging in 0 and 6 pi? Who has it? Anyone have it? What is it? Let's try that. 30 divided by 2 pi t. What do y'all think? If t is 0,